Welcome to your deep dive. Today, we'll explore containers and virtual machines, the unsung heroes of the software world.
Oh, absolutely. It's been quite an evolution, hasn't it?
It has.
Yeah, we'll be looking at how we went from those clunky physical servers to the sleek efficiency of virtual machines. And then, well, Docker came along,
Yeah.
shook things up again, didn't it?
It did. And it's more than just a history lesson, right? We're
Right.
talking real world impacts like um, how companies can build and deploy software faster, more efficiently
Yes.
than ever.
Definitely.
And then there's this whole layer of security considerations we need to think about too.
Absolutely. By the end of this, you'll have a deeper understanding of how these technologies work, why they matter,
Yeah.
and how they shape the apps you use every day.
So let's rewind a bit and
Yep.
go back to the time of physical servers. Picture this. A company wants to launch a website.
Right.
Back then, they needed to buy a dedicated physical server just for that one application.
Yeah, it's almost hard to believe now, isn't it?
It-
That was the norm.
Yeah.
Each server was a standalone unit with its own operating system, fixed hardware resources, and of course a hefty price tag to boot.
It sounds incredibly inefficient.
It was. Imagine having like a giant truck to deliver a single pizza.
Oh, wow.
That's what it was like.
Really?
These servers often ran at like a fraction of their capacity, just wasting resources and money.
Oh, so what about scaling then? If the website suddenly got popular, adding more capacity must have been a nightmare, huh?
It was. It was slow, expensive, risky. If that single server failed, the whole website went down with it.
Wow.
A recipe for disaster.
So there had to be a better way.
There was, yeah. Virtual machines, or VMs, came to the rescue. Think of a VM as a software simulation of a physical computer. You can run multiple VMs on a single physical server, each with its own OS and applications.
That sounds so much more efficient. What made VMs possible? Like, what was the key innovation?
The hypervisor. It's a piece of software that sits between the physical hardware and those virtual machines, managing and allocating resources so that everything runs smoothly.
So instead of like a bunch of single-use servers, you have one powerful server running multiple virtual machines.
Yeah.
It's kind of like, an
Yeah.
apartment building where each tenant has their own self-contained unit.
Exactly. And just like an apartment building can house more people than individual houses, VMs allowed companies to squeeze much more out of their hardware.
And I bet that resource utilization went way up then.
It did. We're talking a jump from maybe 20% to like 80 or 90% in some cases.
Wow, it's huge.
Yeah. Costs went down. Scaling became way easier.
Yeah.
Need more capacity. Just spin up another virtual machine.
Okay, so what about the security risks then of running multiple applications on the same physical server? Was that a concern?
Absolutely. But VMs address that as well.
Oh,
They
okay.
provide isolation.
Oh.
Each VM is its own little world. So if one VM crashes or gets compromised, it doesn't affect the others or the host server. It's like each apartment having its own fuse box. A short circuit in one unit doesn't cut off power to the entire building.
I see, yeah. But I'm guessing VMs weren't the end of the story, right?
You're right.
Weren't they still pretty resource intensive?
They were. Even though they were a huge step forward, VMs still had some limitations.
Yeah.
They could take a while to boot up, and there was
Uh-huh.
still a lot of overhead from running those full operating systems.
Right.
Remember, each VM has its own complete OS, even if they're all running on the same underlying hardware.
So the search for even greater efficiency continued.
It did.
Enter containers, the next chapter in our evolution of software deployment.
Exactly. Containers took the efficiency game to a whole new level. They're like super lightweight packages
Okay.
that contain everything an application needs to run, the code, the libraries, the dependencies, but without a full operating system.
How is that possible? Don't applications need an operating system to function?
They do, but here's the clever part. Instead of each container bringing its own OS, they all share the host operating system's kernel. It's like everyone in an apartment building sharing the same foundation and basic infrastructure, but having their own customized living spaces built on top.
Oh, that sounds incredibly efficient.
Yeah.
What are some of the other, advantages of containers over VMs?
Well, portability is a big one. Since containers aren't tied to a specific operating system,
Right.
you can move them seamlessly between different environments. For developers, that's huge.
Right.
They can build and test an app in a container on their laptop
Okay.
and know it will run the same way in production on a completely different server.
Right.
So it's like having a modular apartment that you can easily move from one building to another
Yeah.
without any compatibility issues.
And I imagine speed and agility are key benefits too, right?
Absolutely.
Yeah.
Containers are incredibly fast to deploy. They start up in seconds, not minutes like VMs, which is perfect for modern software development, where speed and agility are paramount.
Right.
Imagine being able to roll out new features or bug fixes in a matter of seconds.
Wow.
That's the power of containers. Plus, this speed and ease of deployment makes them perfect for auto-scaling, dynamically adding or removing containers as demand fluctuates, ensuring your applications are always running at optimal performance.
So containers brought greater efficiency, portability, and speed to software development.
They did.
But weren't there some challenges or trade-offs too?
There were. For one thing, since containers share that host OS kernel, the isolation between containers isn't as strong as it is with VMs. If there's a security vulnerability in the host kernel, it could potentially affect all the containers running on that host. That's like if
Hmm.
there's a problem with the foundation of an apartment building, it could affect all the units.
That's a good point. So while containers offer these significant advantages, they also introduce new security considerations that developers need to address.
Right. And managing containers, especially at scale, can be complex. You need a way to orchestrate them,
Hmm.
ensure they have the right resources, manage their life cycles, and handle networking and storage. That's where the story takes another turn with the rise of tools like Docker.
Okay, so Docker emerges as a solution to these container management challenges.
Right.
Let's dive into that in part 2 of this deep dive.
Sounds good.
We'll be back after a short break.
You know, before Docker, managing containers could feel like trying to herd cats.
Oh, wow.
You had all these powerful, lightweight containers,
Right.
but getting them to work together smoothly, well, that was a real challenge.
Yeah, I can imagine. It sounds like Docker stepped in to simplify and
Ah.
streamline the whole container experience.
Exactly. Docker made building, shipping, and running containers accessible to, well, everyone. It's like the difference between trying to build a house from scratch and using a prefab kit with all the parts and instructions you need.
Okay, so how did Docker achieve this? What's the magic behind its simplicity?
Well, part of it's Docker's elegant architecture.
Okay.
It's got these three main components: a client, a daemon, and a REST API. Think of the client as like your command center. It's the interface you use to interact with Docker, telling it what you want to do.
So the client's how we tell Docker what to do.
Right.
Okay, what about the daemon then?
The daemon is like the workhorse behind the scenes. It's responsible for managing all the containers, building images, and handling all the low-level stuff. It's like the construction crew that actually puts the prefab house together.
And the REST API.
That's the communication channel between the client and daemon. It allows them to talk to each other
Okay.
and exchange information.
So Docker streamlined the process of managing containers,
Right.
but what about the containers themselves? Like how were they structured internally?
A good way to visualize a Docker container image is to think of it like a layered cake.
Okay.
Each layer represents a different part of the application's environment.
Mm.
At the bottom, you've got the base image layer, which typically contains the operating system.
So like the foundation of the cake.
Yeah, exactly.
What comes next?
On top of the base layer, you have the application layer, which has the application's code and all of its dependencies.
Okay, so that's like the filling.
Yeah, if you will.
Okay, then what?
Next is the configuration layer. That contains the settings and configurations specific to your app.
Okay.
And finally, at the very top, you have the container layer. This is where runtime changes happen, like files that are created or modified when the application is running.
So each layer builds upon the previous one,
Yeah,
creating a self-contained
Yeah.
portable package for the application.
exactly.
But how do containers actually work their magic? Like what's happening under the hood that allows them to be so lightweight and efficient?
Two core Linux kernel technologies make all this possible: namespaces and control groups.
Okay.
Let's start with namespaces. Imagine each container has its own little world, like a separate apartment in a building. Namespaces make this possible by providing these isolated environments for things like processes, networks, and file systems.
Right.
So a process running inside a container can't see or interfere with processes in other containers or on the host system.
That's a pretty clever way to keep things organized and
Yeah.
prevent conflicts.
Exactly.
What about control groups?
Control groups, or C groups, are all about resource management.
Okay.
They allow you to set limits and priorities for how much CPU, memory, and other resources a container can use.
Okay.
This prevents one container from, like, hogging all the resources and ensures all your applications have the resources they need to run smoothly.
So it's like like having a fair system for sharing the building's electricity and water, as we were talking about earlier. Yep,
Exactly.
makes sense. What about storage? Where does the data in a Docker container actually live?
That's a great question, and it's a common source of confusion.
I bet.
By default, when a Docker container stops,
Okay.
any data stored inside the container it's lost. It's like working on a document in a temporary folder. If you don't save it somewhere permanent, it's gone.
That sounds risky.
Yeah.
What if I need to persist data, like user uploads or database files?
Well, Docker provides a few different mechanisms for handling persistent data, including bind mounts, volumes, and 2FS mounts.
Okay.
Line mounts are the simplest option. They allow you to directly mount a directory from your host machine into the container.
Oh, okay.
It's like creating a symbolic link where changes made in one location are reflected in the other.
So if I edit a file on my host machine, those changes will automatically appear inside the container.
Exactly. Bind mounts are really convenient, especially for development.
Right.
But they can introduce some security risks and portability challenges in production environments.
I see.
For persistent storage in production, Docker volumes are the recommended approach.
Okay, so volumes are like dedicated storage units that Docker manages like independently from the host system.
That's right. Docker volumes are more robust and portable because they're not tied to the host file system. They're typically stored in a specific directory on the host, which Docker manages.
Okay.
And importantly, they persist even if the container is stopped or removed.
So it's like having a separate hard drive that's specifically for your container's data.
Exactly.
What about temps mounts? You mentioned those earlier.
Yeah, temps mounts are interesting because they store data in the host's memory.
Okay.
It's like having a RAM disk that's super fast but also ephemeral.
Oh.
The data is lost when the container stops.
Why would you want to store data in memory, though? Like, it sounds like it could easily disappear.
Well, it's useful for temporary or sensitive data that you don't want to persist on disk.
Right.
For example, you might use a temps mount to store session data or temporary files that are generated during a process.
Okay.
Because it's in memory, access is extremely fast.
Right.
But you know that the data won't stick around after the container is stopped.
That makes sense. So we've got bind mounts for development convenience, volumes for persistent storage, and temps mounts for that temporary in-memory data.
Right.
Lots of options.
Lots of options.
Anything else we need to know about Docker volumes?
One important distinction is between named and anonymous volumes.
Okay.
Named volumes are explicitly created and referenced by a name,
Okay.
making them easy to manage and share. Anonymous volumes, on the other hand, are created automatically by Docker when you start a container with a volume mount without specifying a name.
So it's like the difference between like having a file with a specific name and just saving it as untitled document.
That's a great analogy. And here's the crucial part. If you want your data to persist reliably, you need to use named volumes.
Okay.
Anonymous volumes are more like sticky notes
Right.
that can easily get lost.
Right.
They're fine for testing or temporary situations.
Right.
But for production use, always stick with named volumes.
Okay. Named volumes it is. Are there any other like potential pitfalls or best practices that we should be aware of when we're working with Docker volumes?
Well, permissions can sometimes be tricky.
Okay.
You need to make sure that the container has the right permissions to read and write data in that mounted volume.
Right.
This often involves making sure that the user and group IDs inside the container match the user who owns the data on the host system.
I see.
There's a handy Docker command to set this up correctly, and it can save you a lot of headaches down the road.
Good to know. Good to know. Any other tips for managing Docker storage effectively?
Absolutely. Avoid using bind mounts in production unless you have like a very specific reason.
Okay.
They can introduce those security and portability issues.
Right.
Clean up unused volumes regularly.
Okay.
They can take up space and clutter your system. And if you're working with distributed storage or cloud-based storage solutions, you might want to explore Docker volume drivers. These allow you to integrate Docker with a wide range of storage providers.
Okay. That's a lot of great advice about Docker storage. So, to recap, we've gone from the limitations of physical servers to the efficiency gains of VMs, and now to the incredible flexibility and portability of containers, with Docker emerging as like this key player in making containerization accessible and manageable.
Yeah.
But with all the sharing of resources and the inherent complexity of containerized environments, security has to be a top concern.
You're absolutely right. Security is paramount in the world of containers.
Yeah.
And while containers themselves aren't inherently insecure, they do introduce new attack surfaces and considerations that developers need to address proactively.
So let's shift our focus to the security landscape of containers.
Mhm.
What are some of the key security challenges and best practices that we need to be aware of? We'll explore this in more detail in part 3 of our deep dive. We've talked about the evolution from physical servers to VMs and then containers, and how Docker has made containers more user-friendly,
Right.
but with all this, shared infrastructure
Mhm.
and the complexity of containerized environments, security's got to be top of mind.
It is, yeah. Security is crucial in any software environment, but it takes on new dimensions when we talk about containers.
Right.
The good news is Docker has built-in security features and best practices to help reduce those risks.
Okay.
It's not about being scared of containers.
Right.
It's about understanding the security and putting the right safeguards in place.
Okay, so let's break it down. What are some of the key security challenges that come with using containers? I imagine the shared kernel is a big one.
Yeah, you're right. Because containers share the host OS kernel, a vulnerability in the kernel could potentially affect all the containers running on that host.
Yeah.
It's like, if there's a structural flaw in the foundation of a building, it could affect all the apartments above it.
So what can developers do to address this shared kernel risk?
Well, one thing they can do is choose a minimal base image for their containers.
Hmm.
The base image is the foundation of your container, and it contains the operating system and core libraries. By starting with a minimal image, you reduce the attack surface. It's like building your apartment on a solid concrete slab instead of a complex network of beams and supports. Fewer things can go wrong.
That makes sense. Less is more when it comes to the base image.
Right.
What other steps can developers take to enhance container security?
Access control is really important. You want to strictly limit what a container can do on the host system.
Okay.
Docker provides mechanisms like Linux capabilities, CLinux, and a parmer to restrict a container's privileges.
Right.
It's like having, security guards at different levels of the building controlling who can access which areas and what they're allowed to do there.
So it's all about limiting a container's ability to cause harm if it's compromised.
Exactly.
What about network security? Containers often need to communicate with each other and with external services.
Right.
How do we secure those interactions?
That's a great point. Network segmentation is key. You want to isolate containers into different networks based on their trust levels and communication needs. Docker provides various networking modes like bridge, host, and overlay networks to give you fine-grained control over container communication.
Can you elaborate on those networking modes a little? I think it'd be helpful for our listeners to understand how Docker handles network isolation.
Sure. The default networking mode in Docker is bridge mode. It creates a separate virtual network for your containers, isolating them from the host network.
Okay.
It's like each apartment having its own intercom system. Tenants can talk to each other within the building, but they need to use a different phone line to call outside.
I see, yeah. So that sounds pretty secure.
Right.
What about the other modes?
Host mode allows a container to share the host's network stack, essentially giving it direct access to the host's network interfaces.
Okay.
This is useful for performance reasons sometimes, but it also reduces isolation. It's like removing the intercom altogether. Everyone can hear everyone else's conversations.
I see. So it's a trade-off between performance and security.
It is.
What about overlay networks?
Overlay networks are designed for multi-host communication.
Okay.
They create a virtual network that spans across multiple Docker hosts, allowing containers on different hosts to communicate seamlessly.
Yeah.
It's like connecting multiple apartment buildings with a network of tunnels. Tenants can move between buildings without going outside.
Interesting.
Overlay networks are really useful in container orchestration systems like Kubernetes, where you're managing containers across a cluster of machines.
That's fascinating. It sounds like Docker gives a lot of flexibility and control over container networking, allowing developers to balance connectivity and security. What about the security of the container images themselves? Earlier, you mentioned the importance of minimal base images, but are there other security considerations related to container images?
Definitely. You want to make sure your container images are free of any known vulnerabilities.
Okay.
Docker offers security scanning tools that can analyze your images and flag any potential issues. It's like having, a building inspector come in and make sure everything's up to code. Regularly scanning your images for vulnerabilities and patching them promptly is essential.
Okay.
And when you're pulling images from public repositories like Docker Hub, It's crucial to verify their source and authenticity. You don't want to end up with a counterfeit apartment full of hidden flaws.
That's a great point. Don't just trust any random image you find online.
Yeah.
Always make sure it's from a reputable source.
Right.
So we've covered a lot of ground today, from, the evolution of software deployment to the nuances of Docker and this critical importance of container security.
Yeah.
Is there anything else our listeners should keep in mind as they explore the world of containers?
I'd say the most important thing is to keep learning and exploring. The world of containers is constantly evolving, with new tools and technologies and best practices emerging all the time. So stay curious, experiment with new ideas, and don't be afraid to try things out. That's how you'll truly master this technology and unlock its full potential.
That's great advice. So if our listeners want to, dive deeper and get some hands-on experience, where should they start?
There are so many resources available online.
Right.
Docker's own website has excellent documentation and tutorials,
Yeah.
and there are tons of online courses and communities dedicated to containerization. And don't underestimate the power of just experimenting. Spin up a Docker container, play around with different commands, and see what you can create. It's amazing how quickly you can learn by just diving in and trying things out.
Well, I think we've given our listeners a lot to think about today. From the humble beginnings of physical servers to the, incredible power and flexibility of containers, it's been quite a journey. And with Docker leading the charge, the future of containerization looks, well, brighter than ever.
It really does.
Thanks for joining us on this deep dive.
It was my pleasure.
We hope you enjoyed exploring the world of containers and Docker with us. Until next time, happy coding.